Hi everybody and welcome to the first programming lecture of our pneumonia classification project. In this lecture we will pre-process our dataset. You can obtain the complete dataset from Kaggle. Please take a look at the download instructions in the corresponding Jupyter notebook. Before we start, I would like to express my appreciation to Xiaozong Wang and his colleagues for creating this dataset. Feel free to take a look at the linked paper to get more background information about the dataset. I have already imported the necessary libraries for this notebook. We are going to use pathlib for convenient path handling, PyDicom to read DICOM files, NumPy to store the pre-processed images, OpenCV, or as it is called in Python, CV2 to resize the images, Pandas to read the provided labels CSV, Matplotlib to visualize some images, and last but not least, TQDM to get a nice progress bar. We will start this lecture by reading the provided label CSV file. To do so, let us define a variable called labels and then use pandas.read_CSV where we pass the path to the labels file. In my case, since I'm working in the same directory where the images are, it's simply the file name stage2_train_labels.csv. Note that depending on your working directory, you need to change this path. Additionally, depending on your OS, you either need to use Unix style paths or Windows styled paths. Now let us take a look at the first 6 entries of our labels data frame. As you can see, this dataset consists of a unique patient ID, the coordinates where pneumonia occurs, and a binary target variable that indicates whether a pneumonia is present in the given X-ray image or not. Note that there is one entry for each pneumonious spot in an image, therefore some patient IDs occur more than once. As an example, index 4 and 5 correspond to the same image. As our goal is to train a classifier and not a detection model, we will remove those duplicates in the next step. To do so, we simply override our labels variable with the result from labels.drop_duplicates, which accepts a column name, in our case patient ID, as its argument, and then deletes all rows whose contents have already occurred in the specified column. Alright, now we don't need to worry about those duplicates anymore. Now let us create at first a root path, which takes a path object to our train images. The directory is called stage2_train_images. Additionally, let us define a save path, which also takes a path object to the place where we want to store our processed files. In my case, I simply want to use a directory called processed. Now it is time to look at some example images. To do so, we create a 3x3 subplot to visualize 9 X-ray images paired with their corresponding labels. At first we create the figure and axis objects and then use plt.subplots again. We pass the number of rows and columns and the figure size, which is 9 by 9 in this example. We define our loop counter variable c and initially set it to 0. Now we can code the double nested for loop in the range of 3 and then start reading the files. At first we have to extract the patient ID from our labels data frame. To do so, we create a variable called patient_ID and then extract the seed patient ID. To do so, we can either write labels.patientID or use the string patient ID as its index. Now we simply write labels.patient ID, then we call .ilog to get the cth row. Perfect. Now we need to somehow create a path to the DICOM file of this patient ID. Let's store this in a variable called dcm_path, and then we use our defined root path and concatenate this root path with our extracted patient ID. Note that when using pathlib, you can simply combine paths by adding a slash between them. This is really comfortable. Last but not least, we need to add the file extension .dcm to this path. To do so, we override our DICOM path by calling the with suffix function provided by pathlib. So we write dcmpath.with_suffix and then pass the file extension. We have now the full absolute path to the corresponding DICOM file and can read it. Let us write DICOM equals to pydicom.readFile, and then we pass our DICOM path. Additionally, as we are only interested in the pixel arrays, we can directly extract the pixel array. We can store the label or the target variable for this particular image in a variable called label and then extract it from our labels data frame. Note that I use the other possibility here to extract something of a pandas data frame. We simply need to get the cth row and use again ilog for this. Perfect! Last but not least, we simply need to visualize the image and use the corresponding label as its title. So let's get the current axis object by using ing as the indices and call .imshow on our image. Additionally, we set the color map. You can either choose color map equals to gray or color map equals to bone. That's really your choice, just decide what you like better. I will use bone here. Second, we set the title of this corresponding image by getting again our current axis object and calling the function set_title, where we simply pass the label. Last but not least, we just have to increase our counter variable and are ready to run this cell. As you can see, we get a beautiful 3x3 grid visualizing some X-ray images. You can see that the central images of the middle and lower line have a positive label, which means that those patients suffer or suffered from pneumonia. Now it is time to actually load and pre-process our data as explained in the previous lecture. We loop over all patient IDs and standardize and resize those images before storing them in their corresponding directory according to their labels. Additionally, we compute mean and standard deviation of those images as explained in the lecture. Alright, let's get started. At first, we define our sums and sums_squared variables and initially set them to 0. Now we can define the loop over all patient IDs. To decide if the current image belongs to the training data or is used as a validation file, we can use the enumerate function. By getting access to the loop counter variable c, we can put all images from X-ray number 24,000 in the validation split. Additionally, let us use tqdm to get a really nice progress bar. The final loop now looks like this. For c, patient_id in enumerate of tqdm of labels.patientid. At first, we need to extract the full path to the DICOM file. Let's reuse our code from above to do so. We can simply copy the following 4 lines and paste them here. As our goal is standardization, we directly divide the pixel array by 255. Next, as the original images of shape 1024 by 1024 are way too large to be handled by current deep learning architectures, we resize them to a smaller shape of 224 squared. To use less space when storing the images, we convert them to float 16. Alright, let us define a variable called dcm_array. Then we call cv2.resize, pass our pixel array as the first argument and the desired width and height as the second one. As mentioned, we directly convert it to float 16. Now that we successfully pre-processed our current X-ray image, we should store its label in a variable called label. We can simply reuse the code from above to do so. To decide whether we want to store our current image in the train or the validation directory, we define a variable called train or val, and then assign this variable the string train if our counter variable c is smaller than 24,000, else we assign the string val. Perfect. To save our pre-processed files in the correct directory, we can define a save path variable which points to the correct place. Let's call it current save path and then assign our predefined save path followed by the train or validation string and finally the class label. Please note that pathlib cannot handle integers and therefore we convert our label to a string. As we did not create this path before, we need to make sure that it actually exists. Therefore, we access our current save path variable and call the make directory or mkdir function where we pass at first parents equals true. This guarantees that makedir creates all parent paths up to the file. For the second argument, exist OK, we also pass true. This prevents the function from throwing an error if the path already exists. Now we can use numpy.save, where we pass at first the current save path, followed by patient ID, which will act as the file name. The second argument is finally our pre-processed DICOM array. Awesome! The last thing we have to do is to update our sums and sum squared variables. But before doing so, we need to compute a normalizer which takes the number of pixels in each image. In our case, this is simply 224 by 224 pixels. Next, we need to make sure that we only update sums and sums squared while we are in our train split. It is crucial that the validation data has absolutely no influence on the training set. Otherwise, our model might also overfit on the validation data, which basically means that we have no way to validate and evaluate our model properly. Now we can finally update our sums variable by adding the sum of the current DICOM array divided by the normalizer. To update sums squared, we at first square all pixels within our DICOM array. Next, we compute the sum of those squared pixels and finally divide it by the normalizer. Awesome! Now we are ready to run the cell. Depending on your hardware, this might take some minutes, but as we used TQDM, we get a really accurate time hint. The last step remaining is to convert our sums and sum squared variables into mean and standard deviation respectively. We can get the mean by simply dividing our sums variable by the number of images in our train data, which is 24,000. To compute the standard deviation, we take the square root of sums squared divided by 24,000 and then subtract the squared mean from this result. Last but not least, let's have a look at the mean and standard deviation. Congratulations! Everything is completed. This just computed mean and standard deviation will be used in the next lecture to normalize our dataset. Thanks!